Hello, everyone. Welcome back to the morning session. So, for our first speaker this morning, I'm very happy to introduce Shunsuke Takagi from the University of Tokyo, and he's going to tell us about uniform bounds on F signature. Uniform positivity, even better.
Yes, thank you very much for the introduction. It is my great pleasure to give a talk in this conference. So current mathematics has influenced me very much. When I was a graduate student, so I read a lot of papers concerning a flash mass singularity or multiplier ideal test ideal and Fujita conjecture and so on. And I think I first met her in 2002 when I was a third-year graduate student, and at the time I had only one favorite. But she kindly invited me to the special year program at MSRI, and that opportunity gave me a great deal of encouragement. After that, so I had a chance to visit another almost every year until 2010. Yeah, after that I become busy, so I could not. I really appreciate her support and the inspiration I received from her work. And yeah, thank you, Karen. Okay, now let me start mathematics. Today I will talk about the F signature. First, so let me record the definition of F signature. So my ring A is F finite and local. Just for simplicity, as I assume domain, and also just for simplicity, let me assume that reductive field is perfect. So reductive field is perfect. Let's do characteristic. Then, so I consider maximal number of free copies of A in a probabilistic shroud of FE A. So which means M doesn't have a free direct sum. So yeah, AE is the maximal number of free copies of A appearing as a direct sum of FE star A. Then now I give a definition of F signature. Which was introduced by Hofstad-Lasky formally. Hugh. KK, sorry. Formally, but I think it's already implicitly it's already appeared in the work of Smith and Van der Waals. So the definition is a signature of A is defined to be a limit of A sub E over B to the E. D is the dimension of A. E goes to infinity. Okay, yeah, this is the definition. And I give a few remarks about it. So F signature, so limit always exists. So this already, existence of limit already discussed somehow in this paper, but existence of limit proved by Kevin Tucker in for generality. Kevin, can you see this one? Yes. Then, F signature is positive if and only the ring is stronger. This is due to our work. plus t. Okay, now I consider modulo p reduction. So I change the notation. My ring R is a quotient ring of polynomial ring over C modulo R, and I take localization. Okay. And just for simplicity, so I assume y has integral quotient. Okay. Then, so considering mod p questions of Fy, so you have a map. So yeah. So yeah. Anyway, so you have a natural map from polynomial ring over Z to polynomial ring over Fp. Just taking mod p. Yeah, just taking mod p quotient. So then my ring R mod p is quotient ring of polynomial ring over Fp divided by F1 mod p Fr mod p. And again, so we take localization. So I call this ring as a modulo p reduction over R. So this is modulo p reduction. Then my first question is, you can consider the limit of F signature of modulo p reduction of R equals to infinity. So this, does this exist? Yeah, I don't know the answer, but I give you some example that is due to. This example is due to so R is defined by x cubed, is defined by x cubed plus y cubed plus z cubed plus double cubed, and again I take localization. In this case, maybe let me write here. Limit of F signature of modulo p reduction of R is equal to 1 over 8 according to him. So I never computed it, so I trust him. Anyway, so in this case, so limit exists, but in general, so I don't know limit exists or not. So in this talk, let me define a signature of R existing to the limit of a signature of modulo p reduction of R. So this is the definition in this talk. Okay. Sorry, maybe I should. Sorry, I wanted to say R mod, everything R mod p, because later I use R30 for different notions. So this is R mod p. This is also. Okay. Yeah, this is the definition. And okay, and well, let me remind you conjecture. So this conjecture can be viewed as a local version of Schwede-Smith conjecture, which Kevin mentioned in his talk. Local version of Schwede. Which is so let me assume x is spec of R. This is normal. The x is KLT type. And only if modulo P reduction of R is strongly irregular for sufficiently large P. And yeah, I will explain roughly so a little bit about KLT type. So KLT type means so there exists an effective divisor delta. So this is a Q divisor on X, and such that Kx plus delta is Q Cartier, and the pair X and delta is KLT. So this is the definition. So X is not necessarily Q Gorenstein, but Kx plus delta becomes Q Cartier and the pair is KLT. This is the definition. But yeah. And I don't I don't explain the definition of KLT pair, but anyway, it's not important in this talk. Okay? And so let me explain what is known about this conjecture. So this implication, KLT type implies modulo P reduction is strongly irregular. This implication is okay. And the opposite direction is okay if I think it's Q Gorenstein. This is basically yeah, taking in the case of Q Gorenstein, so taking canonical cover, we can reduce to the rational singularity case, so then you can apply current result, and maybe different proof is due to current alternately. But so with that Q Gorenstein hypothesis, this implication is open, I think. And so open even in dimension 3. Dimension 2, so dimension 2, so R become Q Gorenstein, so then it's okay, but in dimension 3, I think it's open. Okay, and anyway, so at the moment, so we believe this conjecture. So then let me go back to this X signature. Then if this X signature is positive, then using the result of Abel-Bahar-Lasky, so this one. So then modulo P reduction of R become strongly irregular for almost all P or all sufficient large P. So then if you believe this conjecture, so this is equivalent to R is KLT type. Okay. So then so the natural question is how about the converse? If R is KLT type, then do we have a positivity of this F signature in characteristic 0? So that is a conjecture due to the Carvajal-Rojas, Javier, Kevin, and Carl. This is conjecture. this conjecture as a CRST conjecture. So then if R is KLT type, then this F signature in characteristic 0 is positive. A conjecture or question here, maybe. I'm not sure.
Can I just clarify something? So when you said that if and only if R KLT type, did you say that that if and only if is only like if you believe the conjecture? So then.
Right. Sorry. Sorry. This part is so. If you believe the conjecture, this one.
Great. Just
sorry.
checking. Yeah. Thank you.
Yeah. We don't know in general, so this is true or not, but. And this means basically, so this means so there is the positive integer c such that F signature of modulo p reduction of R is greater than or equal to c for almost for substitutes large p. This condition is so. So this means the uniform positivity of F signature. Okay. And at least so this conjecture is known. Conjecture CRST. This is okay in dimension 2. So this is easy because in dimension 2, KLT type singularity is equivalent to a finite quotient singularity. And for finite quotient singularity, so there is a formula to compute F signature, so then it's done. But in dimension 3, I think it's open. Of course, there are some special cases, so no, but in general, so in dimension 3, so this is open.
So Shunsuke, can I guess a question just to clarify my understanding? So the point is maybe the F signatures are all positive mod P, but they're converging to 0.
Yeah.
So that
so limit may be 0, so that is a problem. Yeah.
So, but how about where the case when R is Gorenstein? Like when you actually know the implications?
Sorry, about which implication?
So when you actually know the conjecture for R Gorenstein case,
yeah, but still,
even in that case, do you know the opposite direction?
No. So our last key result implies only this implication. So yeah.
But the F signature could be like 1 over P, and as P goes to infinity, it's converging to 0.
Yeah. So
And probably not, but.
Probably. Yeah, I believe so, but at the moment I don't know how to.
Yeah, I think the naive bounds usually have a P in the denominator.
Yeah.
And
I mean, our delta always has it.
and sorry, I always wanted to mention, so this is joint work with Tatsuki Yamaguchi. Sorry, yeah, I always wanted to mention my collaborator. So sorry. So now let me explain our main result. So in this talk we discussed this conjecture. Of course, so we don't know in general, but we can prove some cases. And this is our main result. And, okay. Now we have, suppose we have a pairing extension. So this is a pure local algebra. And I assume around this KLT type, essentially of finite type over C as before. And the pure means for any R modulo n, So this map induces a map from M to M tensor with S, and this induced map is injected. This is the definition of QT. And then what we can prove is if F signature of S in characteristic 0 is positive, then F signature of R is also positive. This is what we can prove. So then we have several corollary of this main theorem. First corollary is ST conjecture, that one, or for reductive quotient singularity, reductive quotient singularity. Here, reductive quotient singularity means if you take a completion of R, then this is isomorphic to the invariant subring of formal power series over C, and where G is a reductive or linearly reductive. It's in characteristic zero, so they are equivalent. So the G is a linearly reductive group acting on formal power series ring.
Assumption only on R, or is it on R and S?
Sorry, yeah, what I mean, so this conjecture holds.
Oh, that conjecture.
Oh, yeah.
Oh, I'm sorry.
So
No.
when completion of R is
Oh, this is
isomorphic.
a theorem. Great. Okay,
Yeah.
never mind.
Yeah, the statement of theorem is this one.
Yeah.
Yeah, because basically, so if you take a reductive quotient singularity, so this become a pure suffering of formal power series ring. So basically, yeah, then we can apply main theorem somehow. And second corollary is again conjecture CRST can be reduced to the case R is Gorenstein. So in this conjecture, so R is just KLT type, so R is not necessarily Q Gorenstein, but we can reduce to the Gorenstein case. This is corollary to it immediately follows from main theorem. So yeah, let me explain how to prove corollary to. Yeah, as S, we take anti-canonical. We take anti-canonical ring, and also we take a localization of anti-canonical ring. So M is a maximal homogeneous maximal idea, homogeneous maximal idea of S. So this is local ring, and if R is KLT type, then and if you apply the famous result of Delta-Cassin Eco-Markana, then S becomes Noetherian. But once we know that S is Noetherian, then S is actually Gorenstein and KLT. So, note that we from R to S, so we have a natural inclusion, and this is a pure. Since S is this. Then we can apply main result, then by main theorem. We know if F signature of S in characteristic 0 is positive, if F signature of S is positive, then F signature of R is also positive. So it is enough to show the conjecture for this S. So that's why we can reduce to the Gorenstein case. This is corollary 2. And the corollary 3, we can also conjecture the RSP can be reduced to the graded case. Original statement is about the local ring, but we can consider graded version. And actually, graded version is equivalent to local version. Yeah, maybe I will come back to corollary 3 if I have time. So first, let me explain how to prove this main theorem. And so there are two key ingredients. So one is local provenance alpha invariant. So this is actually a local version boundless invariant. So Pande introduced a characteristic P analog of Tian's alpha invariant, and we consider its local version. So that is local F alpha invariant. And the second key ingredient is ultra F-regularity. So ultra F-regularity is a notion of singularity in characteristic 0, so defined in terms of ultra products. So I mean, Stoughton's ultra F-regularity, ultra provenance. Sorry, yeah, using ultra provenance. I will explain later, but these two are key to the proof of mean theorem. First, let me explain what is local F alpha invariant. Okay, then. Okay, now our A is a strongly irregular ring, a strongly irregular local ring, and then local F alpha invariant of A is defined as the infimum of F threshold of X times normalized order of X. And X runs through all elements of maximal area. And here, so this is normalized order, which means this is a maximum integer R such that X is contained in the integral closure of M to the R. This is integral closure. And okay, let me write here. So FPR threshold is, yeah, Kevin already mentioned, but let me give a definition. So FPR threshold X is a superimum of T such that the pair R and XT is strongly irregular. So then, what is the definition of strong irregularity for pairs? So that is, okay, this condition is, I also give a definition of strong irregularity for pairs. So this means for any non-zero C, sorry, my ring is A. So yeah. For any natural element C, there exists an integer E such that first we consider E times iterated Frobenius map. After that, I consider multiplication by 3 times x to the round up of t times e to d. Yeah, it's a bit complicated, but this composition map split. This is a definition of strong F-regularity for pairs. And okay. So then it is easy to check if our invariant is between 0 and 1, and also if A is regular, then this invariant is equal to 1. This is very easy. Okay, and basically important stuff is the following. This is basically due to context. We just localize her argument. So yeah, again, our ring R is characteristic 0, so essentially all finite type over C, so something like this. Okay. So then we define the F signature of this R, and this R is positive, and this F signature is positive if and only if limit inf of alpha F alpha invariant of R mod P modulo P reduction of R. So this guy is positive. So positivity is equivalent. Value are not equal, but positivity is equivalent. That is important. And let me denote this limit by alpha FR. So this is a F alpha invariant in characteristic 0. So the problem is reduced to prove this local F alpha invariant is uniformly positive. And then, in order to prove positivity of this guy, we use ultra regularity. Okay, now I introduce ultra regularity, but in order to introduce ultra regularity, I have to explain a little bit about the ultra product. So then maybe the P is a set of 4 prime numbers, and I consider a family of rings indexed by P. This is a family of rings. Then ultra product of AP, which is denoted by A infinity. This is the ultra product of AP. Is defined to be a direct product of AP modulo some equivalence relation. And yeah, I will explain this. So
Sorry, can I ask a dumb question about the definition? So this alpha inherent, is this characteristic or mod P reduction of actually the case stabilities P and alpha invariant?
No. Yeah, Pandey proves so
that's
yeah.
That's not the case.
Yeah. Yeah, usually so if you reduce to positive characteristics, you may have more divisors.
I see, but it still kind of in principle measures the singularity of the anti-canonical divisor in the worst possible sense. Is it? Or that number?
Yeah, it's not so clear, so I still, yeah, we don't know much about this invariant. Yeah, and so let me go on. So then, the sequence AP is equivalent to BP if and only if AP is equal to BP for almost all P. Here, yeah, I said a bit cheating. Yeah, this is a bit cheating because in order to justify the meaning of almost all P, I have to introduce ultra filter on this set, but I don't want to do that. So maybe Tatsuki will explain ultra filter thing. So then, yeah, in this talk, let me skip. He's an expert. He's a master of. Okay, then yeah. Anyway, so this is a infinity, and important part so is if you consider the ultra product of algebraic closure of FP, then this guy is non-canonically isomorphic to C. This is non-canonical isomorphic. Then we fix this isom. Then our real R is this, and so we have a defining equation F1 Fr, and whose quotient are of course complex number, but we have this isomorphism. So complex number so corresponds to some sequence of elements of FP bar. So yeah, if you pick one complex number, then you get a sequence of elements of FP bar. So then for each P, so you have a corresponding to element in FP bar. So then basically, if you replace the quotient of Fi by a corresponding number in FP bar, you can get a ring R sub P. Now I use R sub P. So this is FP algebra. Our ring R is of course C algebra, but so using this isomorphism so, and replacing quotient, then we get a FP bar algebra. And R infinity is ultra product of this R sub P. Then, because of this fact, so this becomes C algebra. And similarly, so if you have an element X in here, then you get the element X sub P here by the same argument. Okay. So then, okay, now EP is this is a positive integer for any P. And let me denote epsilon. This is the ultra limit of ultra product of EP. This is non-standard integer. Then, so the following is the ultra property. We have a map from R to R infinity, which sends X to X sub P. So if we have an element X in here, then yeah, as I explained, so we have an element X sub P in here. So then we have an element X P, X sub P, and we take EP. P to the EP power. And sorry. Then yeah, we take a ultra product. Okay. This map is called ultra properties. And using this properties, so yeah, I think so. R is defined over C, and R is indeed also C algebra. So they are in characteristic 0, but still we have an analog properties morphism. So, and using this map, so we define ultra F-regularity.
Do we need to take different EPs, or can we just fix one E and call that F?
You can choose whatever you want to, but for application, we need to
You need to do it for that application,
yeah.
okay, that's what I was asking.
Oh, sorry, what is the equivalence on that? Because these EPs are just numbers in FP part or FPs. No, sorry, EPs are just in Z, right? Or in natural numbers. Natural numbers, yes. So what is that equivalence, or what is the equivalence there?
Yeah, you can consider that a product of
yes,
and so then basically, same thing.
Oh, the same, exactly like AP. Okay.
So okay.
Wait, sorry, can I ask one more question about that? Are we requiring the EPs to be equal for, oh, no, so we're just choosing a random?
Yeah, random, yeah.
Okay.
Whatever you want to. So sorry, I have to mention one thing. So in order to get a feeling about R sub P, I want to say one remark. R sub P is actually as more to P bar polynomial ring over a P bar. So modulo F1 mod P R mod P and take its localization for general for almost all people.
So in particular, that match is surjective R to or R to R infinity. That the maps are surjective.
No. So for almost all people in general, so that R sub P is just a base change of modulo P reduction to the FP bar. So modulo P reduction is originally defined over FP, but R sub P is defined over FP bar. But just for general P, just a base change of modulo P reduction. Okay, then now let me explain ultra regularity. So I choose F sub P in RP randomly. So and TP also positive. TP is positive real number. Yeah. Okay, and our F is ultra product of F sub P, and our T is ultra product of TP. Then, so then this is element of R infinity, not R. F is not element of R. But we say RFT is ultra irregular if for any non-zero element C is in R infinity. So C can be written as a ultra product of
C
CP. There exists a non-standard integer epsilon. This is a ultra product of PP. And I have a map from R to F epsilon star R infinity. Following. So F epsilon is this one. And we consider map sending x to F epsilon star ultra product of P times FP as FP to the CP P to the EP. So it's very complicated, but and F epsilon x. This map become pure. Sorry. Definition looks complicated, but
I have a question about the definition. Are you saying it's independent of the choice of the non-canonical isomorphism?
No. It depends. It may depend.
So it should be like indexed somehow by, it's like ultra F.
Actually, a priori, so definition depends on the choice of ultra filter. Also this isomorphism, but it's no problem for application. But we need to believe axiom of choice, otherwise we cannot take it. Then okay, now okay, so here is a proportion. Okay. So our R is again in characteristic 0. And okay, let me write down again. Our R is like this. And we take TP is positive integer, so positive real number, for every prime P. And our T is a ultra product of TP. And I have an element X in here. So then, as I said, so we have an element X sub P in alpha P. Okay, then what I want to say is that pair RP and X sub P to CP. So this pair is strongly irregular for almost all P. So we have a family of strongly irregular pairs. So this condition implies so X P. This pair is ultra irregular. And the converse is also true if anti-canonical ring for R, so anti-canonical ring over R is Noetherian. So again, this is the case if ring R is KP type because of DCHM. So if anti-canonical ring Noetherian, so we have a converse implication. So basically, so assuming this family are strongly irregular if a non-leaf, so this is ultra irregular. So we can handle the F-regularity, family of F-regularity in looking at a single morphism. So, yeah, this is ultra product, but still this is single morphism, single map. So this is an advantage. So then maybe.
So I have a question about the definition. Is the definition, should that R be, are you defining a pair where R should be R infinity? Or is this condition on R or condition on R infinity? What's your F-regularity?
But R infinity is defined by R, so then, I mean, yeah, this element is not in R.
Yeah, that's what I'm
So then,
confused.
yeah, maybe, yeah,
That's what I'm
it's a problem of notation, but yeah, you can, yeah, yeah, if you want to, you can say something like this. But yeah.
Well, the reason I'm worried is because it also depends on the isomorphism and the ultrafilter and all that stuff, so I don't know if it makes sense for R.
But the source of that map is R, not R infinity.
Yeah.
Source is R. That's what.
But R maps after you fix all the isomorphisms to R infinity, and then it factors through that, so that's why I was confused. Like, you could just as well put R infinity there.
Yeah, okay, yeah, but I think it's just a matter of notation. So
Yeah, I see what you're saying, right?
Yeah. Okay, yeah, so using this, so we have this, so then the following main lemma. So I already erased the definition of F alpha invariant, but so F alpha invariant, the definition of F alpha invariant involves the FPR threshold. So then following is important. Again, we have this is a pure local shear algebra. Around this essentially finite over essentially finite over C, and we have an element X here. Then a pure threshold of modulo P reduction of R, and I also consider X mod P. Yeah, we consider this guy. So this guy is greater than or equal to a pure threshold of R mod. Sorry, S mod P, X mod P. For all but finite infinity. Yeah, this is this is the main lemma, and I should have mentioned so. Notice. So we are assuming that this is pure, but since S is not necessarily finitely generated as R module, so R mod P, we have an inclusion from R mod P to S mod P, but this is not necessarily pure. Not necessarily pure. So in general, purity is not preserved under modular P reduction. So that's why this is a problem. And yeah, there's a counterexample, but anyway, so let me skip the detail. This is main lemma, and but as I explained here, so after base change for almost all P, so this R sub P is isomorphic to modular P reduction of R after base change. So we can interpret this condition in terms of condition on RP, something like this. So then, using this proposition, we can again interpret the condition in terms of ultra regularity. And so advantage of ultra-regularity, so these are defined in characteristic 0, and we have a pure morphism from R to S, so then, so in characteristic 0, so we use purity, so that is advantage. And sorry, I don't have enough time to explain the detail about green lemma. Yeah, I prepared, but I don't have time.
But this fact right here is why you use the ultra pure, I mean.
This is the reason why
Yeah.
I use the ultra-regularity. Yeah, so yeah, maybe let me write down some, just diagram. So yeah, we have a pure morphism from R to S, and we have some ultra properties like this. And basically, yeah, we have this commutative diagram, and yeah, in order to this implication, basically, so we have a strongly irregular pair on S. So then, using this proportion, we have a ultra irregularity on S. So then, we have some purity here. This is pure. The pure composition of pure morphism are again pure. So this becomes pure. So then, so we have a ultra irregularity on R. So then, using this proportion again, so we get the family of strongly irregular pair on R30. So then, yeah, this is a kind of strategy of this proof. Okay. So then, yeah, finally, I wanted to say something about the corollary 3. Corollary 3 is conjecture can be reduced to the graded case, and so I have only 1 minute, maybe. Yeah, maybe I don't give a precise definition, but you can consider this kind of conjecture. So now my x and delta, this is projective log pan pair over C. Then, so you can consider alpha invariant of x. So now I consider modular reduction of x and also delta. Yeah, I don't give a definition of it. Yeah, but I guess you can imagine somehow. Yeah, you can consider this kind of so Frobenius alpha invariant in positive characteristic. So then, my conjecture here limit in so this line is positive. So sorry, I don't give the definition, but yeah, I guess so. This is a global version of local alpha invariant. So I explained before, and actually, so this conjecture is equivalent to the original conjecture CRST. So since this is somehow related to global irregularity, and global irregularity can be checked by looking at section ring. So we can reduce to the graded case. That's why conjecture is can be reduced to the graded case. That is what I want to say. Okay, okay, let me stop here. Thank you very much.
Question. So you're saying the local conjecture in dimension D
Mhm.
follows from the global, this conjecture in dimension D plus 1?
Okay, it's a bit complicated. So okay, for local conjecture, the dimension D, and so then this is not Q Gorenstein. So now in order to reduce the Q Gorenstein case, so it's a Gorenstein local conjecture. This is somehow equivalent. Gorenstein local conjecture. in dimension d plus 1. Yeah, because we take the anti-canonical ring, so dimension gets higher, and then yeah, basically we consider this, and this is somehow equivalent to the graded conjecture over dimension d plus 1. Yeah, I think. Yeah, we after reducing to Q-Gorenstein case, we basically consider Collar component. So then, so if this is dimension d plus 1, then Collar component is dimension d, and then food section is dimension d plus 1. So then yeah, we have this.
So the whole conjecture reduces to the Gorenstein graded case, is that right?
So yeah, that's a good question. Actually, I want to prove this, but at the moment, so you can reduce the Gorenstein local case, or you can reduce the graded case. I'm not sure because in order to reduce the Gorenstein graded case, so you need to prove Q-Hal version. Q-Hal version is equivalent to the local version, but yeah, but somehow, yeah, by technical reasons, so I don't know how to reduce to the Q-Hal case.
I mean, we don't even know the conjecture for like a graded hypersurface, right?
Yeah, we don't
Yeah.
know.
I mean, that's actually where Suchicha's thesis started.
Yeah.
For some very specific hypersurface.
So, yeah, I have to run MMP to get the equivalent. So then, in the process of MMP, so yeah, I hope it is equivalent to the Q-Fan case, but at the moment, I don't know.
Sorry, this is kind of a naive question. So you have this ultra or UF thing, ultra filter for almost all P's. You have something which is only for infinite unities. Basically, I'm asking, could you do LC or F split, those kind of LC type or F split?
So yeah, but I use ultra irregularity only for the purity statement. So
He wants it to be characteristic 0. So
oh,
if he only has finitely many P's, it won't be.
Yes, then you cannot do that. So that's why I'm asking if you can you do it for infinitely many P's or some technique. I don't know.
I don't know.
This KLT type gives you for almost all P, but LC should be like for infinite many P's.
Yeah, but just yeah, I don't know much about the behavior of F signature. So yeah, F signature is really hard to compute. So then yeah.
Does your work imply, like for an individual prime P, positivity of the alpha F invariant is equivalent to positivity of the F signature?
No. It's yeah, okay, yeah. I have some inequality. So really, what I want to say is we have a A is a strong ratio of dimension D, and EA is just a Hilbert summary multiplicity. Then we have a following, and just my C is a embedding dimension of A plus 1. So then we have a following inequality. This is greater than or equal to F signature of A, and F signature of A is greater than or equal to multiplicity of A times alpha invariant of A to D divided by D factorial. Yeah. If my memory is correct, then we have this inequality, and then I mean
This is an analog of.
Yeah, this is actually fun. Yeah. So that's why I said
This
so.
is
This
degree
is
instead
essentially
of.
due to Pande. And then, yeah, if you're taking a limit basically, so you get a equivalence of a positivity.
Questions? There's an announcement. Oh, yeah. Yeah, let's.